Motion planning in dynamic environments is a major challenge in robotics due to limited computational resources which affect trajectory quality. Although modern GPUs and parallel processing have improved motion planning speed, robots with high-dimensional configuration spaces still face significant challenges. Additionally, the trade-off between complex and simplified robot models introduces further complexity. To address these issues, we introduce a novel motion planning pipeline which uses DRL to train a neural network that adapts nonlinear MPC settings based on the robot's state and its task. In each RL iteration, an action is selected to formulate the NMPC problem. Then NMPC iteratively calculates trajectories which are executed as control commands. The policy network is trained on collected observation, action, and reward tuples. In our design, each observation includes state-related information such as position, volume information, distances, translational, and angular velocities. At each RL step, either continuous or discrete action is selected to formulate the NMPC. Both representations include information to determine the robot model, constraints, and the next target. In the discrete case, we divide each subspace and assign each combination to an action index. We design our reward function based on both terminal and intermediate states. Terminal rewards are triggered when the robot reaches the terminal state. At each iteration, the step reward is calculated as a weighted sum of various reward and penalty terms. To prevent the robot from wandering and encourage efficient model selection, we include a constant penalty based on degrees of freedom of the chosen system model. A reward term based on the current distances between the goal and the robot's end effector encourages the robot to move closer to the goal. We also encourage the agent to select sub-targets by introducing a step target reward. We differentiate between scenarios where only arm motion is active and those where the robot base is navigating. Apart from arm-only modes, the target reward function is designed similarly to the goal reward, except using sub-goal poses. Reaching sub-targets prematurely within the action horizon negatively impacts control flow, so a penalty term on early target arrival is introduced to ensure smoother action behavior. We developed a simulation environment featuring a conveyor belt and a box to be picked up. At the start of each episode, the robot's base pose is randomly initialized within the orange area, and goal positions are randomized within the purple area on the conveyor belt. We evaluated our proposed model across 108 different configurations within the same environment, and each of them was run 5 times to ensure reliability. Evaluation results show that policies trained with Re4MPC achieved higher success rate and fewer failures compared to the baseline. Our approach significantly reduced reliance on whole-body motion planning for trajectory computation, while also generating sub-goals, thus increasing the likelihood of producing feasible trajectories. Moreover, we conducted an ablation study on our target reward design, whose inclusion led to faster training times, higher success rates, less use of complex model in trajectory computation, and more sub-goal generations. As a key contribution, we provide an open source implementation of our work, including the experimental dataset.